20-kilogram child is on a swing that hangs from a 2.6 meter long chain. What is the maximum speed if she swings out to a 49-degree angle? So we have two sections here, the initial position and the final position. Initial position, you can put on either side, it doesn't matter. But in this case, for me, I put on the right side as the initial position. And the final position would obviously be at the very bottom. And it's pretty obvious that you won't find the final velocity here, because after the potential energy transforms into kinetic energy, all the kinetic energy will be released, and after this point, the gravity takes a toll and pushes down the child, resulting to decreasing in velocity. But in this point, gravity doesn't do anything here until right after. So the maximum speed will be here. So we're ignoring air resistance in this problem. So since this problem has a lot of gravity and kinetic, we would use the kinetic energy formula and the gravitational energy formula. So for the section 1 would be in the right, section 2 on the left. For me, in this case, it's easier to read because initial position is on the right and final position is on the left. So you would have to write two separate equations that would equal to each other, because the energy here is would equal to the energy over to the final position. So for section 1, you have to write the kinetic energy formula plus the gravitational energy formula. And for section 2, you do the same thing, but this will be at a final velocity and this will be a final height. So to simplify this expression, since we know that this position has potential energy, the velocity will be at 0 because no kinetic energy. Therefore, if you plug in this equation here for the kinetic energy formula for section 1, if you plug in 0 here, this whole equation would be 0, so you can cross that out here. And for the final position, since it's at the very bottom, that means the height would be at 0, because since the initial position is up here, the final position is up here, and it's at the very bottom, the height, so it will be at 0. And you plug in 0 for the final height for the gravitational energy formula for section 2. This expression or equation would equal to 0, so you can cross that out here. So rewrite the whole expression here. We move on to here. So it's saying that the kinetic energy formula is equal to the gravitational energy formula. Well, this makes sense because since it's just all gravity here and there's no kinetic energy here, it wouldn't make any sense that there's no kinetic energy here as for section 1. And since there's no height for the final position, it would make sense that there will be no gravitational energy since height isn't involved here. So it'll make a lot more sense if this expression would be kinetic energy formula would equal to the gravitational energy formula. So to isolate the final velocity, because that's what we're finding here, we will divide the mass by both sides, and the mass will disappear because 1 over 1 equals 1, and it's redundant. So we write it, and it would be 1/2 times velocity squared equal to gravity times the initial height. And we're isolating the final velocity for the next few steps. And next, you would have to multiply 2 by both sides because we're trying to isolate again the final velocity. And with 2 times 1/2 equals 1, and you multiply by 2 on this side too, then we equal to velocity final squared equals to 2 times the gravity times the initial height for section 1. So we would square root the velocity squared, because when we want to get rid of this squared here, and the final velocity would equal to square root of 2 times the gravity times the height, or initial height, I should say. So we only have one variable here in order to find the final velocity, which will be gravity, but we don't have the initial height. So if we redraw this diagram, so the final position will be here, the initial position will be right here, but we can see that we can draw a right triangle in order to find the initial position. Because since we know this whole chain is 2.6 meters, this means that we can use two numbers, and if you add them together, it will equal to 2.6 meters. So we redraw the whole triangle here. You will know that the initial position or initial height plus this variable, which would be the question mark, would equal to 2.6, because to move on, or to go back into the original diagram, we can see that the child's initial position would equal to this position here. So to find this side, or since we already drew the right triangle, we can use trigonometry in order to find the adjacent side of this triangle, or adjacent side of 49. So we can use cosine, because you will need the adjacent and the hypotenuse in order to find this side here. So we would use the hypotenuse, which would be 2.6 times the cosine of 49 degrees, and we equal to the adjacent side of this triangle here, and it would equal to 1.70575 meters. And we subtract the 2.6 meters, or I should say 1.7 meters subtracted from the 2.6, and we equal to 0.89424, because you will have to subtract 2.6 minus the 1.7, and it will equal to the initial height. So to plug in the variables for the final velocity, we plugged in the gravity and the initial height. Then we square root the entire thing, or we will have to plug in the variables for this equation, and it will be 2 times 9.6 meters a second times 0.8424 meters. Then we square root that, then it would equal to 4.1865. But the least amount of significant figures of this problem will be at 2 sig figs. So convert to 2 sig figs, round up for this answer would be 4.2 meters a second, and that would be the final answer.